introduce Mrs. Padmaja. She's a postgraduate in industrial engineering from IIT Delhi. And you're all aware that IIT is a premier institute of technology. It's a lot of children covet to go to the IITs. She's worked in the US, Singapore, Malaysia, Mumbai, Kolkata, Chennai, and Hyderabad, and executed projects for MNCs. But I think she finally yielded to her passion, which is teaching, and took up teaching. She taught an international school in Hyderabad before she went on, along with her husband, to start a school called Crosswords in Guntur. She has a versatile personality and has a passion for history and art. She's an avid reader and has amassed knowledge on world and Indian history, contemporary literature, social awareness, child psychology, pedagogy, and latest trends in the field of education. So I think it's a pleasure, and it's a rare treat for all of you to be, a part of a lecture by Mrs. Padmaja. I want you to make the most of it, children. Listen to it intently, and you can follow through with your questions at the end of the session. Right? Any doubts here? Class 8 and 9? All of you?
Auntie.
No, auntie.
No, auntie.
Right. So we've got about 18 participants here. How many more are we expecting? We've got a few more. Okay. I think about... Radhika, can you put out a message on the WhatsApp once again? Yeah, I think Padmaja, let's get started. We are recording the session, so the children who join in will see the recording. Yeah.
Thanks,
Good morning.
Anita.
Good morning.
Yeah, good morning. And that's quite an exaggeration from your principal, but still, thanks here. And yeah, you are all very pretty and beautiful. I don't know, even some of you have not turned on the videos. You're good. I'd like to see pretty faces in the morning. All right? Yes, Kartikeya, Virtual. Ashish, Anirudh, Yashwan, Yuva. Probably you're having your breakfast, no problem. Okay. So you all belong to 9th class or 8th class, no?
9th, auntie.
9th. Very
I
good.
think
Okay.
combination of 8th and 9th here, Padmaja. Yeah, sorry.
Okay. So yeah, I've chosen a pretty related topic to your class. It's easy also. Most of you can relate to this very easily. So this 1 hour, we're not going to get into any technicalities of the physics of gravitation and all. Simply, we'll just superficially touch what is gravitation, how to understand it when you turn the pages of the textbooks and all. Okay. So, all right. I hope you all have had your breakfast already. Right? Okay. Fine. Just if you don't want to turn on your microphones and all, just give me a thumbs up if you want to say yes to anything. All right. So we'll use some whatever sign language to proceed. All right. So is there any child or any one of you who's really into physics? Just trying to understand. Anyone who's already into other advanced topics of physics. Your principal ma'am was telling me that some of you already are into coding, right? Okay, so I assume that you might have studied some of these topics already, but still, okay, let's touch upon this topic. What is gravitation? But before that, let's do a little bit of time travel. Who likes to time travel with me? Okay, I'm going to share screen. Actually, children, I don't mind if you are all unmuted because we're not a very big group. I think we can manage with our microphones on also. Okay, just check if you have high noises on your side, then mute yourself. Because I'd like to have an interactive class rather than, because this is not any regular class, regular formula and all. So I'd like to have a conversation rather than a class. Okay, so you all hear me?
Yes, Auntie.
1 second. Okay, okay, good. So you can have your mics on. So that will be more exciting. Nice. Alright. So let's go back to 1665. Okay. So can any one of you tell me what is happening in India in 1665? Who was ruling India? A little bit social, let's say. Who was ruling India in 1665? Any idea?
Not sure, Auntie.
Emma?
Jahan.
Shah Jahan. Yeah, just about right. It was like, Shah Jahan already, the throne was taken over by
Yes,
Aurangzeb.
Aurangzeb.
Yeah, and it was Aurangzeb who was ruling India at that time. Okay, and what else was happening in India at that time? Suppose you know Calicut, Bombay, all the ports. Something was abyss in India. Something different was happening in the southern ports of India, especially. What was happening? 1665. They were traders from all over Europe. French traders, Dutch traders, English traders. Okay, especially English traders have taken permission from whom? Which king? Jahangir. Right?
Jahangir.
So, yeah, so that is the social scenario in India. Okay, let's move a little westwards and see what is happening in England. You know the first Queen of England, Elizabeth? Elizabeth has died, and the England kingdom was ruled by her, the son of her cousin, okay, James. All right. So in England also, monarchy was going on, and they were sending ships and troops all over the world to occupy and colonize the entire world. So that was the social setup of the entire world in those days. Okay, and of course they were colonizing, trying to colonize America too. So this is a scenario. Let's see what's happening in one of the prestigious universities in England. Do you recognize this university? You might have seen a lot of pictures. This is a very, very old Oriental University of England, established by the kings themselves. This one is Cambridge University. What is so special about 1665? Just the way the schools were closed and you're all sitting at home and attending classes from home. Of course, there was no online classes in those days, so the universities were closed in 1665. What form? Can you guess? Some of you maybe know. Same as now. Now we have Corona break, right? COVID-19 is happening. In that year, plague, bubonic plague was happening in France, UK, and Europe, most of the places. So they have shut down the universities, and children, all the students have gone home. Okay, so here comes our hero, who's this? Everybody knows this one, right?
Yes.
Who's that? Who's sitting under the tree?
Isaac Newton.
Newton. Sir, Isaac Newton.
You know this picture from almost like 5th class onwards, right? The apple falls down, and the story everybody knows. But why is he sitting under the tree? Why isn't he in the college? Just the way you are at home, he is also at home because the college is not open, it is shut down. Okay. Now tell me, how many of you have sat like that and thought of things that are going on around you? Like Newton.
Actually.
If you're doing something special just now, I heard from your ma'am that you're doing hobby sessions. You're trying to reach out to the little children and
Yes, auntie.
Yes, ma'am.
take them under your
Yes,
wing,
auntie.
right? Yeah, you're doing very, very useful things and a very, very good initiative. All of you, I really appreciate this. Okay, you've reduced the burden on the teachers and also you're doing a very good job. Okay.
Thank you,
Similarly,
auntie.
Newton, he returned home. He had a farm at home, so his mother wanted him to work in the farm and become a good farmer. But obviously, he has gone to college, and 1665 going to college is something, right? So
Yes,
he didn't want to come back to farming. So what he is doing, he's neither working in the farm nor going to college, but he's sitting in the tree and just observing things. So all of a sudden, this apple falls down, and what did he deduce? What did he understand? What did he say? Yeah, he somehow understood that someone, or somebody, some force is pulling this apple towards the earth. Okay, so that's what he called as. What did he call it as? He called it as gravitation. Got it? So gravitation, this apple is being pulled towards the earth. Okay, so later on he tried throwing many things and whatever things from a height, and he did notice that this is happening for everything, every mass, every object, everything on the surface of the earth. Now tell me, how many of you have experienced gravitation, the force of gravitation? Anyone?
Every one of us.
Every one of you. How?
Because gravitation is what keeps us holding on to the earth, or else we would all be floating away.
Yeah, what you experience when you walk or sit on the earth is normal reaction, not exactly the gravitational force. Hmm? Isn't it? It's a reactionary force to gravitation. But directly, have you ever experienced gravitation? Someone pulling you towards the earth. Most of you have, as you said, all of you. When you simply
When we
jump off a
jump,
branch, yes, and you jump off a slide, you jump off a floor. All of you might have done this at least one time, any one point of time. Okay, you're all 13 years old. I don't think you would have grown up without experiencing the free gravitational force. Okay, so yeah, all of us experience gravitation. This is the gravitational force you will experience when you are not in contact with any surface or not sitting anywhere, not standing anywhere. Okay, so as someone said just now, it is Kartikeya or someone said that when you are sitting also you are experiencing gravity. That is a reactionary force to gravitation. We'll come to that little later. Okay, so yeah, suppose it is an apple that is fine. Suppose it's a big boulder, then will the force be much larger? Yes or no? Big one, big massive object. Then will it be, the force will be larger or smaller?
It would be large.
It will be larger. Okay. So, which means that Earth pulls massive objects with greater force. Smaller object, smaller force. Okay. And what about, suppose the apple is not on the tree, but is just flying really, really far away from the surface of the earth. Then will it really get pulled towards the earth with the same force?
no.
May not be. We're not very sure because we are so close to the surface of earth. We all experience the same force, same pulling force, right? Suppose we are very, very far away, thinking in terms of space beyond stratosphere, mesospheres and all, if you are there, then probably Earth may not be able to pull us as strong as we are on the surface. Okay, so but then when you think of gravitation, what is the next celestial object that you think of? Who's the closest celestial object or closest space object to us? Natural, not the artificial satellites. Who's our closest neighbor in the entire space? Yeah?
The moon.
Right? Yeah. So the moon. Okay. The moon is also being pulled towards the Earth. Is it true? If it is true, how come it doesn't fall down into the Earth? Just now we said apple falls down towards the center of the Earth, right? How come the moon is not falling down? It's just going on and on, day and night, years together. Never falls down, never misses its orbit, right? So what could be the reason? If there is so much of gravity from the Earth, it should pull moon also, just like the apple. Apple falls with a certain acceleration, right? Certain velocities. Okay, let's not talk about the technical things like acceleration. Why the moon is not moving towards the center of Earth?
Is it because even the moon has some sort of pull on the Earth, though not of a great extent, it has sort of a pull on Earth.
Right, that's also true. Yes. Okay, moon also pulls Earth, but the extent, the magnitude of force that Earth exhibits is much larger than the moon's, right? So we expect it to fall down on us, right? Where it doesn't happen. But how about the other objects, far off objects like Jupiter or Mercury? How come we are not able to pull those things towards us?
They also have their own gravity.
They have their own gravities. One fact, and the other fact is they are far away from Earth. Okay, they are a finite mass in space, and those objects are really far away when compared to Moon, especially Jupiter, Mars, Mercury. All these things, they are very far away. Okay, see, even a very small mass, Pluto is a very small mass, right? But we're not able to pull it towards us because it is really far away from the Earth. Okay, so what matters for gravitation, for the pull, okay, is that means the mass of Earth, mass of the other object, whatever object it is, Moon, Apple, or Jupiter, whatever. And also, when we sit far away, what is the physical quantity that we are talking about? Distance, right? The distance between the two masses. Yeah. So, in short, the gravitational force depends on mass of our mass, like one object. We are talking about two masses, suppose Earth and Moon. So, object 1, object 2. Mass 1, mass 2. Also, how much different distance they are separated by? The distance of separation. Okay, and usually we measure the separation distance from the center of one object to the center of other object. Okay, so such, but okay, I'll come to the how part now. So what is gravitational force? Can anyone please sum up now? What is gravitation? Anjali. Is Anjali here? In one line, what is gravitation? Simply, it is a
The force that pulls objects towards the center of it.
right. In one way, that's also right. Okay, so yeah, you said center of Earth, right? And just now someone also said that moon also pulls things towards it. So it's not just Earth. So can we
Yes.
generalize it? That
Yes, ma'am.
it's a force of attraction between two masses. Between two masses. They can be big masses, they can be one small mass, one big mass, or both small masses. Any mass. So there is a force of attraction between one object, another object. Any object that has mass, they get attracted towards each other. It depends on the mass of this object, as well as how much distance of separation is there. So, how is the gravitational pull acting? It acts directly proportional to the masses of the objects, and the more the distance, the force. We can say that gravitational force is inversely proportional to distance between the masses. Okay, so this in a sense is what Newton later experimented and found. He just theorized this thing that there is a force that is exhibited by Earth or by any mass, it pulls another mass towards it with a certain force which is directly proportional to the product of masses of the two objects and inversely proportional to the square of distance between the two masses. Okay, so we will not go into the derivation part or the constants that are attached to this formula. So more or less we've understood what is gravitation and how it happens, at what magnitude it happens. Okay, now can any one of you tell me if it is a general, Newton said that this is true for all masses. Okay. So when it is true for all masses, you are one mass, your friend is also another mass. Why aren't you two getting attracted? Do you feel that force of attraction between another object there or another person there? We don't get pulled towards each other, right? How come this becomes the law of Newton, Newton's universal law of gravitation? So, which Newton says applies for every object, every mass, everything that is a mass in this universe. But we don't experience it. I don't feel any force of attraction towards the table. How come? Can anyone of you just guess what it is? How it is different when it comes to us? Any guess? Just any guess.
Ashish, can
Yes,
you unmute yourself and go ahead and answer that. You
it's
can
okay
take a
actually.
guess.
We're having a
Yes, Aunty.
conversation. Did you ever feel that you are standing before a large mountain and you feel pulled towards it? I don't
No.
think so, right?
Not exactly, Aunty.
Why not? Because when compared to the masses that we're talking about in a celestial sense, planets, stars, and all, our mass is minuscule, really negligible mass. We are nothing. The mass of a human or mass of a table or a mountain is nothing when compared to the mass of the entire Earth or Sun or any other big planets. Okay, so yes, this is true. Law of gravitation applies for all objects in this universe. But the thing is, our mass is so small that the force of attraction is also really negligible. Okay, so we don't feel it when compared to the other forces. What are the other big forces that act on us? Bigger forces. Just now you said, no, one of you already told that, gravitational force of Earth, we can feel that. We don't feel a gravitational force from your friend, but you feel the gravitational force from the Earth because Earth has greater mass, it pulls us with greater strength. Okay, the other bigger force that acts on us is atmospheric pressure. Okay, so among all these big forces, we really hardly feel this very very negligible minuscule force called gravitation between among ourselves. Okay, so but it still is there. Okay, now we come to the last question. Why? Why gravitation? Up till here, see what and how is what concerns your lessons in 9th class, as far as I can see. But let's stretch a little more, a little bit forward and see why. Sometimes, suppose, Sriparth pushes Kartikeya, Durga. Let's say, Kartikeya and Durga are playing, and Kartikeya pushes Durga by mistake. Okay? So,
Yeah,
will Durga feel the force?
Yeah, that's their physics science teacher, Mrs. Durga. Yeah, I should have probably
Oh,
named them for your reference. No,
sorry.
no, no.
Hi.
I'll name them for your reference. Yeah.
Okay,
Okay.
No
let's
problem, ma'am.
talk
It's
to
okay.
Miss
It's okay. Just giving
Ashish
example.
and
Yeah.
Ashish and Kartikeya. Let's suppose
Yes.
Kartikeya and sorry Durga.
No, madam. Nothing like that. Everything is science. You can. Whether
Okay.
you or me or biological sciences, that's it. So everything is science. I don't mind for that. Okay. You can carry on.
Okay. So suppose Kartikeya and Ashish are playing, and Kartikeya by mistake pushes Ashish. So what will Ashish feel? What kind of force he feels? This force is coming from Kartikeya's
Kartikeya.
from Kartikeya. What kind of force is he using here?
Muscular force.
Muscular force. Excellent.
Muscular
He is using muscular force. So you feel the muscular force. Where is the muscular force coming from? How come Kartikeya has muscular force?
By his muscles.
He's using his hands.
Yes, he is using his hands and yes, good. So that is mechanical energy. Fine. Where is he getting the energy or the force? What is the force? Origin of that force? Again, you all had your breakfast, right? Ready to have a fist fight. So, yeah, all these fist fights normally that you children have in the classes. Where is the energy coming from? It comes from the food that we eat. Okay, so it is like for every force again there is a background force and there is a conversion of energy from one form to another. Okay, but we again go back to gravitation. When you want to go back to gravitation, can you think of any other force that is driving this gravitational force? Possible. What could be the reason for this gravitational force? Newton as God, okay, he just theorized this, he understood that there's some force, okay, in this whole universe that is driving things crazy, right? Okay, but where is this force coming from again? Did he explain? He could not explain. He did not explain. So that's why he called it as universal law. Just like the axioms you have in mathematics, there's no proof to it, there's no reason to it. You just have to take it as it is. That's called an axiom, right? But here, Newton also thought that this is there, that's it. Just accept it. Okay? So, for why, he did not answer. He said, this is one of the fundamental forces of nature. Okay? So, when something has no explanation at all, then we call it as a fundamental force. Okay? This is something we are getting very close to from physics. We are moving towards philosophy. Okay, what's the reason for this force? The next answer that most of the people might give is God. Okay, so let's not get into that. So physics and philosophy is so closely related. When you ask a why question in physics, okay, you move slowly towards philosophy. Okay, let's come back. So he said there's no reason. It's just there, accepted. So let's call it as a fundamental force. Okay. So can you think of any other fundamental forces of nature where there is this, maybe it's hard to explain, it's there. This causes some other forces, some other acceleration. This will be the reason for many other things. But this will have no reason to look back. Such forces, they have coined them as fundamental forces. There are other things also other than gravitation. If you have already covered the atomic structure, have you already covered atomic structure in chemistry in 9th class? Do you know the structure of atom? Not yet?
Yes, auntie, there's
Yes,
the
auntie.
neutron and the proton in the
Okay, so you
as
already know that.
nucleons.
Okay,
Yes.
very good. So there are lots of forces inside an atom, right? The force of attraction between electrons and protons. Okay, why do they attract each other? Can you explain? All positive forces are attracted towards negative. Okay, and negative towards positive, and positive forces repel each other. This is like they have accepted these things. We don't look for again reason behind this, right? Because there are none. Okay, so this is also another fundamental force. The attraction between positives and negatives. This is called electromagnetic force. Okay, positives and negatives. But there is also one more thing. Within the atom, you see the atom, what is inside the nucleus of an atom? What's inside the
I
nucleus
can
of an
answer.
atom?
What are nucleons? What are present in the nucleus?
The protons and the neutrons
Protons
together are the
and
nucleus.
Yeah.
neutrons, right? Yeah, it's a basic thing that there are neutrons and protons. Obviously, neutrons are neutral particles, they don't have any charge. Protons are all positive charges, right? And they are all closely bound together in one nucleus. How come just now you said all positive charges should repel each other, right? How come they are again bound so closely? What keeps them inside the nucleus? How come they are not thrown outside the nucleus? Because of the great repelling forces among themselves. Is there any explanation to it? There is none. Okay, this is also another fundamental forces of nature. Okay, so we have come across three fundamental forces till yet. One is gravitational force. Second one is electromagnetic force. Okay, the attraction between positive charges and negative charges. And third one is nuclear force. And among the nuclear force also there are two other things, strong nuclear and weak nuclear. Let's not get into it. So these forces which do not have any explanation, they are called fundamental forces of nature. Okay, there is a lot of physics around these fundamental forces of nature. But this was assumed to be so. There is no explanation for the assumption. Okay, it was accepted by everybody till the 20th century. Okay, almost 400 years. No one really, got into the reason behind gravitational force. Why gravitation? No one could explain, and just simply accepted it as a fundamental force of nature. Okay, for 400 years after Newton hypothesized this one. But what happened in 20th century is we had a whole lot of new physicists, and there were a whole lot of new devices, gadgets, instruments wherein physicists can experiment and look into the cosmic world or universe, okay, really far, far away into the universe because of the new devices, telescopes, all these things. Okay, so next, okay, this is like what's up gravitation towards the everything getting pulled towards the Earth is a attraction of the Earth. How moon or why moon goes around the Earth? Okay, just now we thought moon was just going like this, right? And Earth happened to pull the moon towards itself. The moon had its own velocity and Earth pulls it towards itself. So that's why moon always takes a curved direction. It's a constant change in direction of the moon. Hence, it takes a circular path. Okay, we will come back to this slide once again. So, yeah, we covered all these things. I'm just going through the slides. If your apple is here, it gets pulled towards the earth, simply reaches the earth. Okay, if the apple is here, then it simply reaches the earth. But the apple is, our moon is somewhere very, very far off. So the gravitational pull is very slow, very low compared to the pull on the apple. So it will get changed. The direction instead of going straight, it goes, takes a direction change in direction and goes in a circular path. Okay. Suppose moon is not here and really far, far away here or somewhere, then obviously then our gravity will not affect moon. Moon will simply pass away like this. Okay. It will pass away without getting pulled towards earth. If it is here, it will fall down towards earth. If it's anywhere here, it will get into earth because of our gravitational pull. If it is anywhere here beyond this thing, then it will go in its own direction without caring, ignoring earth totally. But it's just about here, something like a Goldilocks zone. They're neither too cold, neither too nor too hot. It's just about in the right space wherein it cannot escape, it cannot fall down. So it just keeps on hovering round the earth. Okay, it's the reason why moon, despite the gravitational force, is simply going around us. Okay. So yeah, what matters? Distance, mass, right? Mass of the second object. Okay. You see Earth and Moon. They are separated by around 384,000 kilometers. Okay, so when Sun also comes into the picture, then both of them get attracted to Sun because of the huge mass of the Sun. Okay. Now, in short, Newton's formula. This is the representative formula that shows the universal law of gravitation. Okay, and yeah, Fg is directly proportional to m into n by r square. M and m are two masses. Okay, to remove the proportionality constant, this how much by how much this quantifying this force was done by later scientist who is named as Cavendish, Henry Cavendish. Newton simply gave that they are proportional to this thing, but the Cavendish also gave the number by how much. Okay, so that capital G is called universal constant gravitational constant. Okay, yeah, we were discussing about the how or why part of the here that. So, what was he saying? Someone what? Einstein did not accept simply that this is, this is something that is there. There must be some reason for why we are getting on pull towards the celestial bodies. So then he simply experimented in his own mind. Okay, Einstein is one scientist who did not use any laboratory equipment or he didn't do any experiments at all. Okay, He's very smart. He just sat in railway stations here, there, everywhere, and then did thought experiments. Okay, so he came up with this one explanation that space is not nothingness. Okay, space is something. Okay, space is something that is like a stretched membrane. Okay, you see the net here. This is space. This is what he perceived space as. That means if you move your hand in the space, then some things are also moving. Like, you are in a web. You're actually in a web called space. Okay? Or it's a stretched membrane. So when a heavy mass drops into that space, what happens? See a big dent here?
Yes,
See
yes,
a
ma'am.
big dent here? That is
Yes.
that's what happens to space when a mass is dropped into space. So every mass in space will move or will pull, will cause a dimple or a dent in the space. This is how we perceive space as. So now, what will happen if some object, some other celestial object like moon is passing by Earth?
It would go through the dent.
Round.
Yes. Okay. It will obviously, it has to move down the dent and reach the Earth. Okay. If it is moving really slowly or if it does not have its own velocity. Either cases, suppose this thing is simply sitting there, then it has to roll down the dent caused in the space. Okay? Or if it is moving really slowly also, it has to go in this path and finally reach Earth. But our moon happens to be going with a certain Goldilocks velocity. Okay, so it neither moves down nor escapes, but it just keeps on moving towards in a circle round the earth so as to keep it safe, itself safe. Okay, so let's see how. See, all these celestial objects, all of us know that all celestial objects must have a velocity. It has an initial velocity that is given by the Big Bang. Right? So all the objects in the space are moving. Everybody is moving. So when it is moving, there are three different scenarios. One scenario is it is moving too fast and too far away. It is moving slow and very close to the any other celestial object. Or it is just about in the right zone of neither far away nor too close. Okay, so three scenarios. Let's see with a demo. Usually I'd like to conduct this experiment in lab every time, but I'm taking a small video. Okay, so this doesn't have a volume, so I'll be explaining this. So objects travel in straight lines through space. Okay, like that. Suppose an object is moving in space, it moves in space without any deviation. But if there is a massive object present in the vicinity of that movement, what happens? There is a dimple, it's a dent in the space. That is called warped space-time. So what will this heavy object cause? Let's see. What will it do? See?
Excuse me, Auntie. Actually, we can't see the video. I can't see the video.
You can't see that. How about the others? No? All of you have a problem or no?
The link is seen, Auntie. That's it. We're not able to see anything.
We are not able to see the video.
Wait. Okay, just hold on. easy now?
Yes.
Yes.
Yeah, we can
Yes,
see.
yes.
Yes, Auntie.
Right. Okay. So if it is moving in a straight line, fine. Then no hindrance, so it moves in a straight line. Nobody will object to its motion. Now, there is a bigger mass sitting there in space. So obviously that will create a dent in the space. So that's going to affect our movement of the moon, let's say. So two objects, they come together. Did you see the deflection in the path of the? Just when it comes near that massive object,
Yes.
then its path is changed. Yeah, that is because of the dent. Suppose it is moving with a slower velocity than that, then it's trying to move in an elliptical orbit around the mass. Okay. This is an experiment, so the white object, the white ball will lose its original velocity because of the friction. In space, that doesn't happen. So it keeps on moving in the orbit. You see, it keeps on moving in the orbit in space. In this experiment, again, it has to fall towards it. So this is our Goldilocks velocity thing. Okay, the velocity is just about right to make a circular path around the massive object. Now the center one is our sun and the moon and earth. You see, the little one is orbiting around earth and that together is orbiting around sun. Okay. Dark energy is nothing but the opposite of the dent. So if we just consider sun, earth and moon, then it is quite simple. But the universe is not as simple as that. There are innumerable objects, celestial objects, okay, out there in the universe. So there will be lots of collisions, lots of masses hitting each other, and lots of masses attracting the other masses, and all these things are happening. So So it is not just one moon, one earth. So many things are there. So how do you perceive the entire universe as one bigger object attracting smaller celestial objects, and then this whole system, like our solar system, is again being attracted by another bigger center of the things like galaxies and so on and so forth. So let's see with a small demo here how that can be understood. Okay. All right, can you see the screen, all of you?
Yes.
Yes, Padma.
Yes, yes, sir.
Yes, Auntie.
Were we supposed to hear the audio, Padmaja? Audio?
Audible?
I think
Sorry, yeah.
No, it's not audible. But
Can
did
you
you
come
enable?
again? Is it Anita?
The audio is
Oh,
not heard.
audio is
Enabled.
not there. Huh?
Padmaja, did you enable
Oh,
share audio when you're
okay.
doing the screen sharing? In the screen share option,
So that's the
this,
problem.
yeah.
Nothing there, no
Can
stars,
you
no
now?
Yes.
Is it audible now?
Yes, it
planets, which would
is.
mean
Yes, it is.
that if an object rolls through that environment, say this is a comet or a planet, it will go in a nice straight line trajectory. But the key thing is Einstein says that if we have a heavy, massive object like the sun, Einstein says that the sun, merely by being within the fabric of space, causes the fabric to curve, to warp. And then other objects, like the planets, the Earth, Mars, and so forth, he says, they go into orbit because they're rolling along the curved environment that the sun creates. This, according to Einstein, is how gravity is communicated from the sun to the Earth, to Mars, to the other planets. This is how gravity works. Now, we did a little version of this demonstration not too long ago on the Late Show with Stephen Colbert. We got a lot of really great response and a number of great questions were asked online. So let's answer the two most frequent questions that people asked. Okay, question number one, Alec.
Why isn't the Earth spiraling into the sun?
Yeah, exactly, right? When you look at the marbles, they're all spiraling into our yellow shot put here. So would that happen to the Earth? Why doesn't the Earth spiral into the sun? Well, the answer is these marbles are spiraling in because they're losing energy, because of their frictional interaction with the spandex. In empty space, there's virtually no friction at all, so planets hardly lose any energy. Now, they actually do lose a little bit because the planets can cause the fabric of space to ripple a little bit. We call it gravitational radiation. So if you were to wait about 10 to the 20 years, 100 billion years, if the Earth is still here, it will, in fact, spiral into the sun. Very good. Second question, Sophia.
Isn't it gravity that pulls the yellow thing down?
Yeah, right? So if you think about it, the reason why our yellow shot-put sun is causing the spandex to warp, it's because gravity is pulling on the shot put, right? So we're kind of using gravity to explain gravity. But the key idea is that Einstein says that the sun, merely by virtue of being in space, causes the fabric of space to warp. That's the key idea at the heart of the general theory of relativity. All right, guys, so that's all for today from the Day Green Science Lab. Science at Home.
Okay, so it pretty much explains, right? Okay. Right, so all this, there are 2-3 fundamental things we need to understand. First thing is, every celestial object has got its own velocity. Okay, from where? From the Big Bang. Okay, and beyond that, there is no explanation till yet. So we start at the Big Bang. So every object has a velocity. If it is moving at a certain velocity and comes closer to another object, which is already moving in the space, then it either gets attracted towards it, joins the other mass, or just about gets attracted and goes around it, or simply gets a small deflection and moves its own way, ignoring the other mass. So if there are thousands and millions of things that are moving in the space, just imagine it's a whole crazy universe going around, round, 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 round. What is going around what? Nobody knows. Okay. So just the way the experiment he has demonstrated, all these things are moving towards a central, the biggest warp in the space. Okay. The moon moves around the warp that is created by Earth, Moon and Earth together moves around the warp created by Sun. Sun again moves around the center of the galaxy. Center of the galaxy probably is it? Can anyone guess? Why Sun together with all his family should move around a particular center of galaxy? What is center of galaxy? By the way, who is sitting there?
Supermassive black hole, if I'm not wrong.
Can you be a little louder?
In the center of the galaxy, is it a supermassive black hole?
Possibly. Okay, so that's the reason why all of us, the entire families and families of planetary things are moving around the supermassive black hole. Okay, what is a black hole? Well, that's a whole new different topic. It takes another 1 hour to cover, but in short, we will come back to what's a black hole. Okay. Now, since we have understood what gravity is, so now we also know the reason for gravity, right? Unlike the previous century people who just accepted it as a fundamental force, now we know the reason for gravity. It's a stiff fabric. Just imagine this base is a very stiff fabric. Inside it, there are masses and masses and masses that's moving, so which is continuously warping the space-time fabric. Okay, so it is like it's like a wavy fabric. Now that you imagine there's so many celestial objects in the space, the entire fabric of space is wavy. It's not straight. Just the name is depicted. No, it is not. It is totally wavy because there are so many objects. Every object creates a dimple in itself. Okay, so yeah, these are some early questions probably we can easily answer. What happens to gravity? Oh, are we out of time?
We're good, Padmaja.
Oh,
Carry on. Yeah, we are good.
just maybe another 15 minutes. So what happens to gravity when it's like away from the Earth? Simple question, right? We move far away from the Earth. The gravitational pull of Earth increases or decreases? Decreases. Because R is in the denominator even as per the formula, or simply intuition says that move away from the center of the mass, the force is less. What happens to gravity when we move towards the center of the Earth?
It decreases. Maybe it decreases.
It decreases or increases? Towards the center. Suppose you are sitting on Earth right now. We are all sitting on. Suppose you get into a mine shaft and then go down. Then, yeah, children.
It becomes weaker and weaker towards the equator.
Yeah. Why weaker? You are moving towards the center, so it should increase, no? Because R is decreasing.
Oh, towards the center. Yeah. It should increase.
It should increase? I'm thoroughly confusing you now. It should increase or decrease? So
gravity should be weaker towards the equator. Maybe due to the other forces like centrifugal forces, kind of thing.
Well. We are not on the surface of Earth actually, and we don't have any. We're not moving. Suppose you are just stationary on Earth, and then later you go down on a mine shaft. You understand a mine shaft? Suppose a mine shaft is, a mine is dug towards the center of Earth. So you're deep in a mine. Deep in a mine means what? Our radius part. You are very close to the center of Earth. So should the gravitational force increase or decrease? The only two answers. Just take a random guess, students.
Come on, children. Take a guess.
Anything.
Sirisha, Sankeet, Tachireddy, take a guess. Rohan Chaudhary. How many of you feel it increases? Thumbs up. How many of you feel it increases? Thumbs up. Okay.
All right. So, but I say that it decreases. Right? Don't look at the formulas. Okay, don't bother about formulas at all. It's not time yet. But for you. All right. So when you move towards the center of it, so clearly you are here, somewhere here. Suppose you're somewhere here. This is very easily understood that gravity decreases. More far away, so Earth can't really pull us. If you are here, then on the surface, then obviously there is a certain gravity. It increases from here to here. It increases. So what happens if you go down deep inside? Then what happens? Just a second.
Padmaja, your voice is not audible.
Not yet.
Not yet.
Yeah, I
Hello?
think the audio is on. Yes.
Hello?
Yeah. Yes.
Yeah.
Yes, Padmaja.
Okay. Right. Okay.
Ma'am, at the center, it will become zero then, gravitational force. G will be
Correct.
zero.
You're there right now. Good,
Yeah,
good,
because
good.
I'll just explain. When
Yeah,
you say
go-
gmm by r square, when it is divided by r square, right? So the
Yeah.
radius over there will be zero. So something divides by zero should be obviously zero. I mean, I don't know whether I'm right or not. That was my blind explanation.
What do you children say? If something is divided by 0, what should happen?
No. It should tends to infinity. But
Infinity.
in general, yeah, infinity.
Yeah.
It should tends to infinity. But gmm by r square is equal to 0 means when you take up 0, then I think it should end up with 0. Is that the reason?
Not quite, because if r becomes 0, then we all know that 0 is in the denominator, then it has to become infinity. That means we have to experience infinite amount of pull towards Earth, but yeah, that doesn't happen. Doesn't happen. Your answer is right. Your reason is wrong. Let's discuss. Okay?
Yeah, reason might be wrong. Yeah.
Yes.
Ma'am, I think the mass is decreasing, right? The mass
Exactly. The mass that influences
mass.
you is decreasing, obviously. When you go to the center of it, how much mass is pulling you? You are already here. You are in the center. So there is no mass that is pulling towards you. Suppose, no, let's not go to the center. Let's go to the middle of the earth. Then what mass is influencing you is only this much.
Yeah.
Okay?
The less
It will
mass
be a
will
circle.
be influenced.
Lesser mass is pulling you. So lesser gravity. If you come here, even lesser mass. So less gravity. Although radius is also decreasing, it doesn't matter because mass is also exponentially decreasing. When you are in the center, then obviously there is no mass of Earth that can pull you. The mass is above you, not below you, so it can't pull you. So that is, it becomes 0. So if you take a curve of, you take a graph of gravity, then your gravity, suppose, is maximum here. As you go far away, it decreases. As we go towards the Earth, it again decreases and becomes 0. So this is how the gravity is when you take it, when you draw a graph like this. Okay, on y-axis, x-axis is the distance thing, y-axis is the value of gravitational pull. Okay, so in terms of formula, they are here, but don't bother about formula. Okay. So now there is also one more factor here. Earth is not perfectly spherical. It is a spheroid. So what do you think? Gravity on pole, compare the gravity on pole and gravity on equator. Which one is more? Yeah. Yeah, children?
Only the volume changes, right? Then only if you multiply and divide it by volume, you can arrive to that formula, right?
Did
Only
the mass
volume
change? Did the mass
mass
of the Earth
doesn't.
change?
No. Mass doesn't change. It's only the volume of a sphere changes.
So
There
it
is no
doesn't
change
matter
in the
to
mass.
us, right? So
Radius,
mass is
Just
same.
if we divide and multiply with the volume, I think you can arrive to the formula. I don't know, but I'm telling, because it is only the volume of a sphere changes, right? I mean, volume of material changes, not exactly the mass.
Okay, so we are concerned about two things here in gravity. One thing is mass of the other object that is pulling us, which obviously didn't change. That you're sitting on pole or sitting on equator, the entire Earth pulls you because you're on the surface. All right, but the distance between you and the center of Earth, which one is closer? If you sit on pole, you are much closer to the center of Earth. That means R value will decrease on pole, which means you
because
will
it's an
feel
oblate.
more. Yes, so you'll feel the higher strength force when you are sitting on a pole than at the equator. Okay, so that's about how it varies with Earth. So I didn't clear anything. I don't know how to erase this. Okay. Yeah, this is bothering me.
I think a clear all would help, Padmaja. Probably there's one. I think
Yeah,
so.
but it didn't give an option.
Okay.
Yeah, there should be one. Ah, clear. Yes. Thanks. So those are the questions related to Earth. Suppose what are the three questions? Pretty much we answered all three questions. Either we go far away or towards the center or sitting on the pole or equator. Now we move on to certain bigger questions like why objects in space are mostly spherical. By now you should be able to tell me, children. I'm expecting at least a closer answer from you. Why should everything be so spherical? Well, if you consider any object in space, every mass or every part is getting attracted to the center of. Yeah. Just imagine any object, Jupiter, anything, asteroids, everything. Okay, so every particle that is present in itself is getting attracted to the center of itself. Okay, so obviously it will pull towards every particle of the mass will pull towards the center of the Earth and eventually become spherical in shape so that the force is equalized on the entire surface. Okay, but certain asteroids are not spherical because of their age. Okay, because of the rotational velocities and all. But most bigger objects you see are spherical in shape because of the heavy gravitational force that acts on all the mass particles in it. Okay. Why do celestial objects move? This we answered already, because they all have an initial velocity from the Big Bang and also from the continuous collisions with the space objects. Can we travel in space faster than today? So we come to the end of the discussion of gravitation. We did a small space travel in the beginning, right? So can we really do time travel? These two questions are related actually. Right now, see, it takes, what's the nearest star first? What's the nearest star?
Alpha Centauri.
Sun. Sun is the nearest star. Other than Sun,
Alpha Centauri.
Alpha Centauri. Yeah, Proxima Centauri. Okay?
Proxima
So,
Centauri.
Proxima Centauri. There are actually three stars in that system. Triple Centauri system. So Alpha Centauri is also, but most nearest is Proxima Centauri. All right. So to reach there, when it takes, even the nearest one, it takes thousands of 150, whatever, thousands of years, or 43,000 years, I think. 43,000 years means it is actually impossible to reach any nearest thing in the space. So, is there a way to get to another system, solar system or celestial system faster than this? How many of you have watched Interstellar?
Yes, and I have. Yes.
You have. Who's that? You know your
Uh,
name?
Kani and Auntie.
Okay, Kaniyan, right? Okay. What's so good about the movie?
It was a little difficult to understand it for the first time when I watched it, so it took me, I think, twice or so to understand it completely.
Even I did so. It's really difficult to comprehend what they have thought. Right? Okay, let's see what they have thought. The nearest star is whatever. So there are so many stars out there, so many systems. Probably there are out there some more Earths which are inhabitable, but we cannot reach them because of the time problem. Okay. Now this is interstellar. Okay, yeah, continue.
Yes.
I hope you got this idea
Yes,
already from
yes.
the
So,
movie, right?
yes, yes.
So the fabric of space, this whatever net you see, that is space. Just imagine the entire space like that. Fabric of space. We already understood that it is totally dented, and there are so many folds in the fabric because of the huge masses sitting in it, and not really sitting, moving in it. Okay, so probably somewhere the fabric is like folded in such a way that a very distant solar system, not solar system, a very distant galaxy or the star system is in one way close to us because of the folds and dimples and dents in the space. Such a defect in space. Who coined this word called wormhole? This one scientist, Nathan Rose. Okay? He actually worked on the works of Einstein. And this space is a fabric, and space-time continuum was proposed by Einstein. Later on, many scientists took up and completed or are still working on this. So he said that there may be wormholes in the fabric of space, so that we can reach from one space, one system to another different celestial system. So this is still a hypothesis. Nobody has tested it out, but there are movies that have come around this concept. Okay, so yes, theoretically it's possible to travel faster than now, faster than today in space, which means we also can time travel in your future. I mean, if Stephen Hawking is right, I wanted to touch upon it. Just keep thinking about it. Is there so much about the solid masses, their gravitation, and all? How about the things, the celestial objects that are not solids, that are still gases, not rings, whatever. Okay, so most stars are in this state. So, do the normal gravitational laws apply to these gaseous stars, gas rings and all? Okay, how is it? How does it work? And now Kanyan has said that there is a black hole in the middle of the galaxy. How did it form? How did it come into existence?
When like we discussed previously, Auntie, the center of an object has the gravitation of its outer body as well. So when a star dies, the star can explode as a supernova, or it can implode to the core such that the core becomes very dense. It makes a huge dent in the space-time fabric.
Very good, excellent. But how come it becomes so small? What happens to all the mass? Will it evaporate? First of all, what is a star die?
When it runs out of energy.
When it runs out of its fuel. Yes, correct. So what is keeping the star in its own shape? The outward pressure created by the fusion reactions inside the stars. Star is full of fuel, okay, helium, hydrogen, and all. Okay, our sun is full of hydrogen and helium, and the fusion reaction is the thing that is producing energy. So this fusion reactions create a lot of pressure inside, so that keeps the sun in shape. And what is pulling sun inside? It's a gravitation. Just like Earth, sun also has gravitation, so it pulls its own masses inside. So imagine a full fireball which is pulling inside by gravitation, which is pushing outside because of the nuclear reactions. So both are balanced, so it is still stable and balanced. But as Daniel said, if the fuel exhausts, this hydrogen helium, this fusion reaction is not an eternal thing. Somewhere at one point of time, the fuel has to exhaust. It runs out of fuel, then obviously the output pressure is gone. When output pressure is gone, the inward pull of gravitation will take over, and then all the mass will come together. But how much it will come together? Not much, no? Because you can have one atom here, one atom here. That's all. How can it become such a small speck in the galaxy? We don't have time to discuss that, but I guess you know the answer. So you can discuss the name with your friends. How can a large star like that become a small speck like a black hole? That many times it can't reduce. Suppose you take a bunch of thermocol balls, a full bunch of them, you can only compress them to a certain extent, not to a speck. How is it possible? That you need to think about it, okay? Think about it, because we are all exceeded time. All right, but yeah. So, can you answer this one single question that appears on your screen? I'm going to put the link here. If some of you can answer, that is fine. Okay, it is a chat box. Okay, that's the link. Just click on the link and give your answer. Oh, good. So I got the response here. Do you think gravitational force is a big force? Can you see the screen? Some of you have answered it as, yeah, 86% say no, 14% say yes. So what's the correct answer? They are a democracy. So let's say no. Okay, both answers are right. When you consider gravitational force with respect to Earth, okay, things on Earth and all, it is a weak force. You are attracted to your friend in a weak way, or towards an object in a weak way. But when you take the celestial objects, it is the greatest of all forces that is driving the universe. Okay, when you study the black holes and all, you'll understand how big it is. Okay, so thanks for the responses. And yes, okay, let's conclude this. Actually, this is a very interesting topic. if you have time, do go about it. Google has so many resources about how stars operate, gravity on stars, and why stars become neutron stars, why they become black holes, etc., etc. And who did all that study? Interestingly, these people, Nathan Rosen is one wormhole, with the post wormhole. Chandrasekhar limit, you might have heard about Chandrasekhar limit. These people are all Nobel laureates, okay? Chandrasekhar, Stephen Hawking, and all did a lot of work on the cosmic things, okay? Wormholes, black holes, gravitational waves. The new concept. Anyone heard about LIGO laboratory? LIGO laboratory, which picked up gravitational waves from a very, very far off supernova explosion. Okay, so just Google and do your research. It's really, really interesting. When the boundaries are gone, physics becomes philosophy. Okay, so yeah, these are the scientists that we adore. These people. Stephen Hawking just said that if we don't look for another planet to inhabit, we'll be gone in a few hundreds of thousands of years. So it is imminent or necessary that we should look for another Earth to inhabit, which means we should understand the space a lot more than we do right now. Okay, all right. That's about my side. Still, I might be having lots of questions, but I don't know. Yeah, please go ahead.
Yes,
Go
children.
ahead and ask
Yeah,
questions.
you can ask
Yeah.
questions. Yeah, we can have you ask questions, children. You can unmute yourselves and ask questions. Yes, all of you.
I quickly want to share something. Padmaja, there is a place, mystery spot in Santa Cruz, California, where I think gravity is zero or something. Hello?
Yeah, Radhika, I think she's resetting her audio.
Okay. Children, whenever you get a chance, please do visit that place.
Or read
It's
up
a
or
wonderful place.
look it up on Google.
The gravity.
Yeah.
Yeah, it's a mystery spot in Santa Cruz where you can really, literally, physically feel how the gravity works.
It's not artificial, it's natural.
Natural. Yeah, it's a natural one.
Okay, okay.
Auntie, what is the name of the place, Auntie?
Mystery spot. It's called Mystery Spot. It's near Santa Cruz.
Right, yeah, we will do some research on that. Right.
Questions, children?
Yeah. Anyone who want to share their own experiences of gravity or whatever space. If you go to NASA and all, you can even feel the so they have a student student tour for students where you can even experience space, gravity free experience in space and all. I think you are hungry. I've held you for longer than.
No. I think Padmaja, you've given them so much information. I'm just hoping that they are processing it and they are not totally blank because
Yeah.
I'm sure there are a lot.
Nothing to remember. Nothing to remember, children. Just no. These are all leaves. If you're interested, do your own full search and extend from there. We are not teachers anymore. Okay, this is 21st century, and we can only guide you a little bit. Rest of it is your effort. So.
All right. Just wanted to ask you that how many of you have felt the interest to understand more about gravity at the end of this session? How many of you felt, okay, now this is something that I want to understand more?